Today we have as our speaker Sachindev Shenoy. He's from Caltech at the Spitzer Center at Caltech. Sachin did his undergrad at Goa University in India. And we were just talking earlier, there's been a big event in India just this past week. Probably some of you are nodding your head, yeah, the launching of Chandrayaan, right? You might think so. That's not actually the case. It actually is that India just beat Australia by 320 runs. In the cricket, that was the worst defeat from Australia's point of view for the last 10 years. So that's obviously a big event for India at the moment. Sachin moved over to the United States and did his work in solid-state physics at the University of Texas, and then moved to Rensselaer Polytechnic Institute, where he did his PhD. And that's where he got introduced to dust in the galaxy and in the universe, and in our local vicinity, in our galaxy. So that's what he's going to be talking to us about today. So take it away, Sachin.
Thanks, Adrian. Hi, that was a nice introduction. Again, I know the audience is very varied. You all come from different backgrounds, so some of the things that I may talk about may be very familiar to you, some may not be, so please stop me anytime in the middle if you have questions, or if you're confused about anything, or if I start talking too fast and get excited and jump around, or tell me to slow down, so that's fine. So MIPSGAL is a survey. It's one of the legacy programs of Spitzer. So Spitzer is an infrared space telescope which was launched a couple of years ago. Every year they have this legacy programs, which are these huge surveys, and what they do is they do a very uniform survey of whatever objects they are interested in, and data is processed, it sits at an archive, and then it's open for the public. Any astronomer or anyone in the world can go in, look at the data, see what it looks like. You can do your science, you can use it to paint pretty pictures and things like that. So today I'll be talking only about the science part, and this is our big team that we have. Though in Spitzer scheme of things, this is really a small team. Legacy programs usually have much bigger teams than this, but just wanted to put everyone's name, make sure that everyone gets their credits, and we have team from all different parts, from Canada, US, Paris, so on and so forth. But the real core team, the people who really worked on this data, are these people. Don Mizuno is in Boston University, and he's the person with Sean Carey. Sean Carey is the PI of MIPSGAL. Don Mizuno and Sean Carey did the bulk of processing. That is, once the data comes down from the space telescope, they have to do a lot of processing, which was done by that. I'll talk a little bit about that later on. They were helped by Kathleen. I'll tell what she did in a bit. And my job in this particular group was to look at all the point sources and make a catalog of it, extract the point sources, make a catalog of it, and in fact remove all the point sources from the mosaic, because we wanted to look at dust and not really point sources, or that's what I was interested in. So this is my brief outline. It will be in 3 parts. First, I'll give you an introduction of what MIPSGAL is, some project overviews. Then I'll talk quite a bit on point source extraction, which is basically my job, my bread and butter, and my baby. And finally, I'll give some of the science. I'll talk a few things on the science that we have been doing. At present, most of this has been done by the large group that I mentioned, and soon it will be available. The data will be available for other community, and of course, the science coming out that from it will be very varied and probably very interesting. But we'll have to wait for that. In brief, historical perspective, 1983, they had IRAS, and this is what infrared picture looked like in those days. You could say, well, maybe there is a point source, a bright source here, but not much. Then we had MSX, and now we started resolving these bright dots. We went to high resolution of IRS, and you could say, there is some extended emissions here seen, but still not very clear. And now we have MIPSGAL, and this is what the image is today. So now we can really resolve all those point sources at 24 micron, and not only that, but now we start seeing structures, those whatever fuzzy, cloudy things in different parts. So this is what we are. So what is MIPSGAL? So MIPSGAL is a survey of our galactic plane. We don't do the entire survey of our galactic plane. If we are sitting in the galaxy and looking at the galaxy, what we do is, if this is my galactic center, then we do a survey of the first quadrant and the fourth quadrant, because that's where most of the dust is, dust and gas is located, and that's what we were interested in studying. It's very similar to the GLIMPS legacy program. GLIMPS was a legacy program from cycle 1 of Spitzer, and MIPSGAL is a legacy program from cycle 2. GLIMPS looks at our galaxy or at our universe in these 4 different wave filters or wavelengths, 3.6, 4.5, so on and so forth. MIPSGAL looks at the same region in 24, 70, and 160, but our proposal or our program was set in such a way that we were just interested in these 2 wavelengths, and that's what I'll be talking about. Today, mainly I'll be talking about the 24 micron project. And the paper for describing how the survey was done, different details of the survey should be out soon. It's already submitted, and please look out for the paper. So here is an image of Msx Image, band E, which is about 21 micron, and overlaid on that, the blue dots are our survey region. This is what we have looked at. So this is, this part is the first quadrant, this part is the fourth quadrant, and this width was about 2 degrees. Here at the galactic center, since we have the bulge and a lot of dust, we extended our survey a little bit higher in B. So here we go from +3 to -3. So that's right. The galactic center part, we do have data for it, but it was done by a different programs. But we have reduced all the data so people can access it. So we have entire data for this region. So our sensitivities or point source sensitivities are something like this. It's about 3 millijanskis at 24 micron. And for those astronomers who don't work in millijanskis, this translates to something like 8.5 magnitudes in 24 micron. And it's about 75 millijanskis at 70 micron. The main aim is to look at gas and dust and look at infrared emissions. All the data products are now available from ERSA, which is the infrared archive. 2 of our main science goals or drivers, which I would want to tell you about, is to look at massive star formations. And in glimpse band or small or low wavelengths band, it's really difficult to look at massive stars, that is stars which are just forming, class 0 stars or even earlier. But when you go to longer and longer wavelength like 24 and 70, you can start seeing those very faint embedded sources which are just turning on and becoming stars. And if you plot this, what we call color diagram, then you can separate out different groups of stars, different spectral types of stars. You can also, this is all modeling data by Whitney et al. You can also look at different inclination if they have disk. Look at different inclinations of the disk and see how it looks like. So once we have the data, we can create a diagram like this and look at what kind of star formations we see, what are the spectral types of star that are coming out, what are their disks masses, how big are these disks, so on and so forth. Some of this I will talk when I mention this in my science topic. The other thing we wanted to look at is energetics of interstellar dust. You may or may not know, but PAHs, which is polycyclic aromatic hydrocarbons, they have emission in the 8-band IRAC channel. So all the emissions or most of the emission that you see in 8 micron images are mostly due to PAHs. You can say the same thing at 24 micron, but in 24 micron, it is very small grains. These are really tiny sub-micron size grain which emit in 24 micron. And in 70s, it is both the small grains and big grains. Here I have shown image from Flagey et al., where they do SEDs, basically spectral energy distributions of different things. Here the black line is massive star formation region, and the red line is the normal ISM. And as you can see, if you look at 70 microns here, they are very different. Note that they are on log scale, so there's a lot of difference in what the physics is of these grains in these two different regions. So once we have these kind of data, we can start looking at individual objects in our galaxy and see what kind of is the SED like normal ISM SEDs, ISM is interstellar medium, or is it massive star formation or something else. So we can start building models and looking at different models. So these were the two main science drivers. This is what we wanted to achieve.
Sachin,
yes?
when you say very small, what sort of sizes of grains are we talking about?
Things like 0.25 microns or smaller. Those are anything from 0.25, 0.4 microns, that region. So here is the data that we have. I've tried to put everything in one slide. It is difficult, but we tried. This is from the first quadrant, and we have a similar one from the second quadrant. If you want more information about our project or want to look at detailed regions or something, you should check this out. It's mipsgalipac.caltech.edu. This site has both for astronomer information and for non-astronomers. So very briefly, we have two-step processing, the basic calibration and artifact mitigation. I will show some of the artifacts. The basic calibration should be pretty familiar to most of the astronomer, bias subtraction, droop corrections, flat fading, so on and so forth. We had to change a little bit. SSE has a pipeline. SSE has already built the pipeline. So they get the data from the spacecraft, put it into the pipeline, it goes through it and gives us the processed image. But it's an automated thing. It's made for, it's not specifically for a given project or looking at one particular science or something. So we had to change that a little bit, which we fixed. And then we had to remove all the artifacts. Since it's a survey, if there are bright sources, then there are artifacts on the image, which I'll show you, and those were removed. Most of this work has been done by Don Mizuno, and his paper is submitted, so more information can be found here. So here is one of the artifacts I want to show you briefly. So if I have an extremely bright star, then when I do the observation and when I have the data in my hand, we see this faint sources. These are called latents, and these are the bright latents, and they survive in the first part of the data processing. We can remove those things because we know how bright these guys are. So if you know what the triggering pixel brightness is, that is, if you know how bright this source is here, then you can estimate what the brightness of this is. What's the brightness of the first latent, the second, third, so on and so forth. Since we have a very good handle on this, we can go back in our processing, look at all those bright sources and say, I want to remove this because these are fakes, these are not real. And that can be removed. Similar things, I'm showing before and after processing images. Before processing for all the artifacts, you can see there's a bright source sitting here and it generates all these small dots. After processing, everything is gone. We have things called discontinuities. When there's a bright star, you can see this line going across it. This is the discontinuities between different observations. When you stitch it together and do an overlap correction, those things disappear off. There are some serious things like jail bars, which you see, even those can be corrected. So Don has done an excellent work to go through all this data. It's a huge amount of data, and doing this is not trivial. And most of these things has to be done in an automated fashion. You can't sit and go through each bright source. There are too many bright sources. It's just not possible. So what is available? We have the input mosaic, big mosaics, 1 degree by 1 degree. We have the uncertainty images, coverage, masks, so on and so forth. Important thing to note in this is the units are megajansky per steradian, and the pixel size or the image that you see on sky is 1.25 arc seconds. This is my work. This is what I have been doing for the last 3 years. When Sean first offered me the job and he said, hey, Sachin, you have to go and do this point source catalog. It's basic photometry, nothing big deal, but you may have to build a pipeline and things like that. I guess I was just out of grad school and I was pretty cocky. I'm like, oh yeah, 6 months, I'm done. And it's 3 years and I'm still working on it. So. But it has been a lot of fun and it has been very educational. Now I understand what it means to go into these big projects and do these kind of things. Anyway, here is the pipeline in a very brief outline of a pipeline that we have, that Sean and the group and me, all of us have contributed and developed. What we do first is remove the background, because as you know, I need to know the exact flux and the position of the point source. And as you saw in some of the previous image, there are a lot of background emissions, the diffused emission. So we need to remove all those things, get rid of that, and start looking for sources. So first we detect and extract all the bright sources. I'll show you in a minute why we have to do that. And then we detect the faint sources, we join those to list and then do the extraction. And then it goes through some quality controls, which I will show you in terms of pictures rather than this pipeline. So the way you do it is you have some models. You have a model of a star. This is called a PRF, which is point response function. What it says is if I have my instrument, a CCD chip, in this case MIPS, and I have a point source, a star, if it falls on this part of a chip, how does it look like? And in 2-dimensional, it looks like something like this. And if I take a cut, it will be like a Gaussian with some wings on it. I'll tell you in a minute why we need to have 2 different filters. But what you do is you go on your data, you look at the point source, you detect the centroid, the peak, and then use this to fit and estimate what is the flux, how bright it is. So here is an example of what the background looks like. This is the original image, and you can see all the point sources sitting around, all the stars or asteroids or whatever. And then you have all these fuzzy objects. Now when you detect, you can mistake these small fuzzy things to be point sources. So you need to get rid of this. In different panels here, what I've shown is it's a filter that we apply to the data here to remove off all the bright the extended emission. If the filter window is large, then you'll see they are still left with a lot of backgrounds. But when the filter window is small, most of the background disappears off. Now you have only the point sources, and you can go ahead and do your processing. Look at the center of the point sources, see where it is in RN deck, use a PRF, and measure what the flux is. But since I have removed this background, or essentially in other terms, what I say is, since I have filtered this image, I need to use the filtered PRF. If I was playing the same game here, I would have had to do unfiltered PRF. But we use the filtered PRF to detect that. So background subtraction is done, and then we'll start looking at the bright sources. The reason you do that is, again, when you look at the bright sources, these beads are called the airy rings. This is due to the diffraction from the optics. When the starlight goes through the optics, it gets diffracted. These are the diffraction patterns you see. So these small, faint things can be confused since it's an automated system. The automated system cannot tell you the difference between this bead, which is a diffraction thing, and this faint source sitting here. So if you start detecting faint sources, you may confuse these things for faint sources. So what we do is we detect all these bright sources, and we mask the images. We mask all the faint sources, which means now we are left only with the bright source. We can go do our faint source detection and detect all the faint sources.
Do you just use a straight threshold there on any pixels above this?
Yes. Exactly. Pixels about a certain. We did a lot of benchmarks to see where is the boundary between what we call bright and faint. Somewhere about 250 millijanskis is our threshold. Everything below that we consider faint. Everything above that we consider bright. Yes?
So why do you mask it instead of just subtracting off? Because it seems like you're eliminating data for faint sources that are in the diffraction range.
Come again?
So right now you're masking off the diffraction pattern.
Right.
Right? If there was an actual faint source in the
Yes.
diffraction pattern,
Yes.
you lost it now.
We have lost it, and we will lose it, and for a couple of reasons. First thing is, when we looked at our data, we didn't have so much crowding. it's not that crowded. For example, in IRAC bands, if you go to 3.6 micron, there are a lot of crowding. There are lots of stars. They have that problem. But at 24 micron, we don't have those problems. I definitely agree. Since this is a huge survey, there will be some sources which will be lost, and that will, for those sources, we'll have to do something else. We'll have to use two different PSFs to fit it and extract it.
Why would you just subtract off the diffraction function, then you would have the point sources left? Instead of just masking them out completely, why would you subtract it?
Good question. We tried doing that a lot, but for some reason we could never mask off we could never subtract the diffraction ring perfectly. And I think I know the reason, but I'm not 100%. When we do the detection, we remove the background, we subtract the background. When we subtract the background, it also removes some of the flux of the star. So when you estimate the flux for this thing, if you are just doing a subtraction of the airy ring, the flux has to be exactly accurate to get the airy ring. That is not possible in this case. So we do that. And then, of course, when we go back, this is just a part one of the question. When we go back to get the sources out, we have not masked the image. We still have the entire source. This is just the detection part of it. The extraction part of it comes next. So we join those two images. We take the filtered image to make a detect table. We take the filtered image and extract the sources. We use the filtered PRF I already mentioned. There are no background fitting because we have all removed most of the background. We don't do blending, as we were just talking about. We have one PSF, one point source per detections. And then we have to scale this extract flux because, as I mentioned, we removed the background, which means we also have removed some of the source flux. The way we decide how much that scaling should be is something like this. We look at all the sources that the MIPS instrument team looks at as calibration sources, all the calibrated stars. They have a very good predicted fluxes. So we observe all those things, use our pipeline to see what the flux looks like, and then we see if there is a scaling between them. And obviously there is one, and the scaling is something like this. So you use this scaling to get the extracted flux up to the predicted flux. So here is the image I'm showing where this is before and after. This is the image we started with. In this case, I have removed all the background, and then I have subtracted all those point sources. So what is left is just the residuals. If the residuals are too high, then the extraction is not very good. If the residuals are small compared to the noise, of course, then the extraction is good. This is not important. And this is what we are all very proud about, that we have been able to achieve. And again, the before and after picture, but here the background has been left off. So we have just removed the point sources from the mosaic. Now one could go here and do all kinds of science on these extended emissions that you see. This is a small, nice region with not too many extended emissions, but in other parts of my talk, you'll see this becomes interesting. So people who are interested in looking at stars can go ahead, look at our point source catalog and study each and individual star. People who are interested in dust and gas, they can go and study this kind of mosaics. Both these mosaics are delivered to the IRAS and should be available available in the archive. As of course, we do have problems. One of the problems is what we call these false detections. These sources, these things in the blue are not real point sources, but they are extended objects. And when we go and fit our PRF, obviously we have issues. The way we detect these guys is to go back and look at the source subtracted image. If it's a point source, it gets subtracted very nicely. There's just some peppery pattern, which is just due to the noise in the data, but this is what it looks like. But if it is an extended object like this, then it comes out with these holes in the center. So we can look at that holes and say, hey, these guys are not really stars, so don't remove them, keep them back in the mosaic as it was. We do the same thing with the saturated sources. The saturated source, it's exactly the opposite case. They come out with very high or bright residuals. So we measure those residuals. We make a ratio of residuals to Poisson noise, and it looks something like this. So anything above 3 or below 3 is thrown out, or in fact kept in the mosaic. The rest are all subtracted. So how good is the data? To do that, we matched our data with the glimpse catalog, and we did a simple search of 5 arc seconds between the glimpse catalog and the MIPSGAL catalog. And here is the number of matches versus the distance. And as you can see, it peaks at something like 0.85 arc seconds, which is not bad at all. And if you think of, is there random matches in my data, then the number is very small. So most of them are genuine matches, and our astrometric accuracy is 0.85. We can increase this, we can decrease this, we can make it better, but that will probably come in the second version of the catalog.
So why is glimpse considered better than?
It's not better than, it's just it came before us. So 2MASS, which is JHK bands, they did their surveys, and they made sure that it's always you build up on the previous data set. The previous data set go through a lot of this data processing. All the data validation is done. So they go and look at it as astrometries and see how good or bad it is. So you know how good or bad that is. So the 2MASS was a very good data set. Its astrometry was very accurate. It was down to a couple of milli arc seconds. Glimpse built up on that. They did their surveys, merged their entire catalog with 2MASS, and they had similar kind of astrometries. So then the MIPSGAL comes, and now we compare it with Glimpse and 2MASS, and we build ours. So that's for astrometric accuracy. What about photometry? How good is our photometry? We looked at one of the star forming regions, M16, and what we have plotted here is the MIPSGAL flux versus the MSX flux. They have a little bit of different wavelength, the peak wavelength of the band. So we have corrected for the color corrections. And that equation described here is appropriate for star forming region. So if this is true, then most of our data points should lie along this cyan in green line. And of course, you see that is true almost till about 1000 megajansky per steradian. That's where it starts going up here a little bit from the theory, and then here it cuts off. So this part is mostly due to the point sources. If we remove the point sources, then it will be straight. And this processing was done even before, as soon as we got the data to look at how good the fluxes were. And this cutoff is because we have a saturation. We have a saturation at about 1700 megajansky per steradian.
How sensitive is your comparison to the dust model? If your grain size model is different for your color correction?
At that wavelength, it's really, the color correction at that wavelength is really small. It's not too much of a difference. We, I guess, just want it to be consistent. I mean, it's 0.01 or something, the difference in color that time. But we just want it to be consistent, so it was done like that. We also played another game, which is we took all the K0 type stars and A0 type stars, and these guys have predicted fluxes at 24 micron from different spectral template. So we looked at the colors of that, the predicted color at 8 minus 24 minus the measured colors, what we have between Glimpse and MIPSGAL. Now, if the world was perfect, then this would all have to be 0. There shouldn't be any color excess. But obviously, this is real life, so you have scatter. Now, if you look at these 4 objects, we later found out that 3 of this were variable stars, and this was binary stars. So if you look at color excesses above -2, that is these guys who are real K0 and A0 type stars, they have an difference about, or excess about -0.03, which is really small. It is inside the calibrations or the cross calibration between IRAC and MIPS. So we are pretty happy with it, but there will be a difference between our accuracy is off by about 0.03, which is not bad. The last thing we'll look at is completeness and reliability. That's how complete is our survey, or how reliable is this data? Can I trust these things? And that depends a lot on which region you see. Here I am plotting a region. The way we do this is we take a region of space, remove all the sources from there, and we have simulated sources which we throw on it at random. The fluxes are random, the place where they fall is random. Then we run the pipeline and see how well we have done, how well has our pipeline looked at their position and fluxes. This is a region where there is a lot of background emissions. And of course, if you look at complete or reliability, we have like 80% or 90% reliability when you go to flux of 60 or 70 millijansky. But for other regions, it increases. And when we come to regions far away from the galactic center where the emission, the background emission is not so high or not so structured, we reach 95% within like 10 millijanskys. So the user has to be careful to look at what kind of backgrounds you are interested in and then see if the data is trustable or not. All this information will be in the catalog, so you have this. So conclusion in data processing is we have done this, we have done the processing, it's available for, and in the archive, people can go and start playing with it. We have used the pipeline to extract point sources from other regions like Cygnus X and so on and so forth, and it seems to be working perfectly fine. So there are still a lot of improvements to be done, but that will come in the second version. We have very good source fluxes and astrometry and photometric data. Okay. In brief, science that we have done, or that can be done, this is the data from just the first quadrant of our galaxy. So here I have plotted the glimpse color versus the glimpse and MIPSGAL colors. So we have something like 1.3 times 10 to the 6 sources in this region. This now can be used to classify different sources. Class 0 objects, which are the youngest objects, they're just starting into forms with disks. They all fall in this region, class 1 and 2 here. Asymptotic giant branch stars here. What I am personally interested in is the stars which will fall on this region. That is, stars which have almost 0 colors at 3.6 and 5.8, but they have excess in 24 micron. What that means is, if you look at the stars in this wavelength band, 3.6, 5.8, they look like perfectly regular stars. But excess is in 24 micron, means they have a dust shell or a circumstellar disks around it, but these disks are more like planetary disks. They are Vega type stars, where they have a dust disk, but the dust in the disk is much more bigger. They are much more bigger than micron size. And the only way those dust can survive there for a long time is from collisions of asteroids and comets. So that dust gets replenished. So those objects are called debris disk objects, and we go about trying to find them in the following way. Here I plot mostly the glimpse data for our sources, for the MIPSGAL sources, something about this number. If the sources are fainter, if our point sources are fainter than 14.5 magnitudes now, 14.5 magnitudes, then there is a high probability that the object that we see could be a background galaxy and not the point source. But in this region, there is very less chance that it could be a galaxy. Nevertheless, there are some galaxies, and we can remove them. We can identify those galaxies. The way we identify those galaxies are, these galaxies are called power-rich galaxies. That is, they have a lot of polycyclic aromatic hydrocarbon, and they emit a lot in 8 micron regions. So you can look at those things and get rid of this. There are 2 different color diagrams here, looking at different colors. But the bottom line is, if it has a lot of emission in 8 microns and they look like galaxies, throw them out. You'll see that the number here keeps on decreasing, because now we are doing all this, what particle physicists say, data cuts. We are removing data which we are not interested in. Then we go ahead and look at only the IRAC colors or sources. If they were all, and most of these debris disk objects look like stars, so we are interested in sources which are just lying about here. We are not interested in any of these other sources. So you do those cuts and remove most of those data. You do the same thing with 2 mass, because remember, glimpse has been combined with 2 mass, so we have 2 mass colors. So you play the same game, remove those data out. What you are left with is something like this. So here I have J minus H, K minus 24. All the sources that lie in between these 2 lines are debris disks object, and we have in the first quadrant something like 8,000 debris disk object. To give you a rough idea, till now, the known debris disk objects are well-known debris disk objects are something about 200 to 300s. That's the known debris disk people have been following. Now you have a huge data set of debris disk object of candidates which you can go and pursue. Of course, there's caveat. It's not perfect. This method that I have described does find debris disk object, but it also finds Herbig AE stars. But then it's easy to find which one of these. If you look at the optical spectra of these stars, they are very different. So I have a collaboration with a couple of people where we are going to go take a subset of this object, because there's no way I can observe all this, or I'll be doing it for next 2 lifetimes of mine, I guess. So we are going to go look at the subset of this, about 100, 200 stars, get the optical data, see what statistically how many are debris disks and how many are Herbig AE. That information itself will be a new science. That's never been done before, and now it's possible to do with that. That's what I have been pursuing.
What's that band that runs through the sort of light band?
This one?
Yeah.
Uh,
It's dark on the top and then it's dark on the bottom.
Yeah, this is a little bit due to reddening. If you look, this should almost be straight if it was all stars. But this thing, what you're seeing is due to the reddening. So you can de-redden this data back here. So these are where the intrinsic stars will sit, and all this is due to the reddening. I mean, I don't know if this band that you see is real or not, or if it tells you anything or not.
It's like 2 populations, sort of.
Yeah, it's
Upper stuff and the lower stuff.
Yes, this one. Yeah, there definitely is. I'll have to look more into it. I'm not sure if at this point I can say what those two, if they are really 2 populations or not. I have other plans where to do the modeling of this thing, and the way it is done is you create a dust model. Since these are not the same dust as interstellar dust, these are bigger dust particles. You can model those dust and have a different grids of SEDs with different physical parameters, and use your data to fit and find the best fits. This work has been very successfully done for YSOs by Barbara Whitney and Tom Robitelli. It basically is based on their methods. I've been collaborating with them to do the same thing for our debris disk object. And the reason you do this is once you have the fit, you can talk about how much grains are, what's the mass of the grain, what's the inclinations of the disks, and talk about real physical parameters of these things. And this
Does it depend on the inclination?
It does. As you change the inclination, you are looking at a different population. So the 24 micron flux moves up and down.
Because the debris disks are optically thin.
They are optically thin, and that's what, in fact, this data which is plotted now, all the grids that have been plotted are for optically thin disks. In fact, it would be excellent. As you see, this is the 2 mass colors, J, H, and K. These are IRAC, and this is 24 micron. We have not yet finished processing the 70 micron data. And as soon as we have the data, it will be better constrained. The disk will be much more better constrained. Oops. Asteroids. Erin Ryan, who is a graduate student in Minnesota, she's been working on this mostly. When we were thinking about surveys, Sean also thought about, we will be going through the ecliptic, so there is a high probability that we will probably see some asteroids, and we wanted to make sure we identify those asteroids. So what we did is the survey was done in a scan mode. We'd look at a part of a sky, we would scan down, and then scan up, move to the next part, scan down, scan up. But the scan down and scan up were separated in time by 3 to 9 hours. So if there were something that was moving, especially main belt asteroids, you would see them move. So this is the original image where both the scans have been fused. But if you take the 2 scans and subtract from each other, you get something like this. Once you clean them up, you have something here. So most of the sources which are real stars, which don't move, appear something like this. They have like a dipole kind of shapes, but they are the same place. But objects that move, you can clearly see the dark and the bright counterpart since you are subtracted. The same thing goes here, the faint ones. So now, for the time when we were observing and we knew, or there was The known asteroids were 683. We used this method to detect all the 683 asteroids. These were known asteroids up there. But then Erin started finding all new asteroids, and at present we have a count of something like 203 asteroids, and she's still working on some of the data. So this is going to increase. Most of these are main belt asteroids. We can look at star formations. In massive star formation, there are two competing theories, I guess. One which is called the triggered star formation versus the another which is the core collapse. The idea is if a star is forming due to an external agent, external triggering, the star should form at the edges of the shock. So what's happening is there's this huge exciting source far off here, OB type stars, which is sculpting this dust cloud that's sitting here. So these are the sculpted dust clouds you see. And the color coding here is the blue is 8 micron, the green is 24 micron, and the red color is 70 micron. So in 70 micron, you can see very young stars, and as you can see, we have many examples of this star forming pillars where the 70 micron is embedded deep inside the star. So this may be an indication that that star formation occurs not due to triggering, which should have appeared somewhere on the edges of the cloud, but it could be from the internal accretion processes. But there is a lot of work needs to be done. One of our postdoc, Nicolas Billot, he's leading most of the work in this region. All of this work is in progress. So what I'm going to tell you now is just partial stories. The full stories will come out in a couple of months when the papers get released. When MSX survey was done, people saw a lot of these dark objects in our galactic plane. They were called the infrared dark clouds. They have extremely high visual extinction about 70 or 40 to 100 magnitudes. It's also known that these dark clouds are the birth sites of high mass star formation. So there is a lot of interest in these things. Sean and me are more interested in extinction part of it, or looking at dust part of it. The usual way to study these dark clouds, or in the past, have been to look at background field stars. So if I have a cloud and a star sitting behind it, I look at that star and see what happens as it goes through, or as the light goes through the cloud. We can't do that for these guys because the extinction is so high, we don't see any background stars. But we are fortunate enough to have this extended emission from the galaxy, which is all around it, and you can use that as a background source and build an extinction map. How much of the light is get absorbed or scattered, and you don't see it. So this is an extinction map. It's really in infancy. We are just starting this work, so this is very crude image, but you can trace column densities, that is densities of particle along the line of sight on small scales, like 2 to 6 arc seconds. Lot of discoveries, mostly in 24 micron. Here again, it's a 3-color image with glimpse catalogs, and you can see the sources, the stars in the center with the dust shell around it. We believe this could be due to Wolf-Rayet stars. I know in the audience there are people who have done this before, so you may find more of this. And we have identified about 200 in this survey now. There are also dust shells which have been seen, and there are indications from previous studies of Morris et al. That this could be supernova remnant. They went and looked at some of these dust shells, and they had a spectroscopy, infrared spectroscopy, and they saw the oxygen emission lines. And they determined that. And the beauty of this is seen only in 24 micron. It's not seen in 70 or in the IRAC lower wavelength bands. We do have Francine Merleau, who is a staff at SSE. She's been looking at all the galaxies that you can find in our survey, and she has a bunch of it. The paper is already out, should be available. But most of these galaxies are unresolved, extremely small. They are below our limit of 1 millijansky, our detection limit. Remember, our detection limit is good down to about 3 millijansky. So this is very faint, but you can at least have a census of how many galaxies are there along the galactic plane, or as far as our data goes. And then there are all the unknowns or interesting objects, so-called. This is Sean's code. There is at least one interesting object in a square degree, and that's true. There are lots of these things. Some of them are extremely different, weird shaped. We don't know what these are. These needs a lot of follow-up to do, submillimeter observations, spectroscopy to determine what these guys are. So in our catalog, the final catalog, which includes both the quadrants and the galactic center, we have something like 2.9 million sources. These are the amount of debris disk candidates that we are interested, or I'm interested in following. There are quite a large number of asteroid detection. All the other is work that is being continued, should be fun. What can we do next? We have to improve the point source catalog. As you saw, even though the astrometric accuracy was 0.8 arc-second, we can increase or decrease that number by doing something called pointing refinement. That needs to be done, which I'm not sure if I'll get to do it, but we'll see. Then we have to finish the 70 micron processing, which is taking us a long time. There is a lot of trouble with removing artifacts and processing. So that will be a next big project for us. We had to do follow-up of all these objects from various other observatories and facilities. The one thing that I'm really interested is to look at all those small extended sources, not the point sources. Point sources are fun for some, but for me, dust and gas is more important. So to make a catalog of all the extended sources, and we'll need some expert system to do that because there are thousands of them in our survey, and to do a follow-up spectroscopy to find what those objects are, what are those things, and what's the physics and chemistry there. As usual, this is one of the ad talks. So there are two websites, one for MIPSGAL, one for Glimpse, and you can go and look at our maps there. If you do happen to go to the AAS meeting in January, definitely look for the MIPSGAL poster. I'm writing this that, yeah, it is really hard to miss it because the poster is big, and it's really big. It's 3 feet wide it's 3 feet by 180 feet. So it will be there. You won't miss it. Okay, it's big. It's really nice. It's impressive.